All right, welcome to the Explainer. Today, we're tackling a massive historical gap in mathematics. We are going to bridge the divide between pure algebra, the world of equations, and pure geometry, the world of shapes. And to do that, we really need to master the fundamental building blocks of this bridge. We're talking about varieties, specifically varieties of both types, affine and projective.
To anchor our discussion, we're diving straight into Robin Hartshorne's absolute classic, affectionately known as the Yellow Book. If you've spent any time studying algebraic geometry, you definitely know this cover. It's essentially a rite of passage for math graduate students everywhere. It is dense, it is brilliant, and today we're going to unpack its core foundations together.
Now, to avoid completely overloading ourselves with these dense concepts, we're going to follow a pretty clear structural map today. We'll start with the algebraic geometry bridge, explore affine space, define an affine variety, and then upgrade to projective space to define projective varieties, before wrapping up with exactly why these varieties matter so much.
So let's start with this algebraic geometry bridge, bridging intuition and technical math. Why do we even need to build this connection in the first place? Well, what's genuinely fascinating is Hartshorne's own admission right in his introduction. He explicitly notes this huge gap separating intuitive ideas from the highly technical language of modern research. He actually writes that his bias is towards classical geometry because those classical shapes provide the geometric intuition, which motivates all further developments. Basically, if you want to understand modern, abstract technical math like scheme theory, you absolutely have to master the classical intuitive shapes first. And that brings us to exploring affine space, looking at the standard coordinates. This is our baseline, the mathematical environment where these classical shapes actually live.
Okay, so affine n space. It's the set of all n tuples of elements, like a1 through an, within a fixed algebraically closed field. Now, you can just think of an algebraically closed field as a sort of mathematical playground where every single polynomial equation is absolutely guaranteed to have a solution. Simply put, this is your standard everyday coordinate system. It's like a typical video game map. Whether you're on a 2D plane or 3D grid, every single point in this space has an exact fixed address.
Right, so what exactly is an affine variety, and how do we get these shapes from equations? Now that we've set up our standard space, the crucial next step is figuring out what kinds of shapes we can actually draw inside it using pure algebra.
But before we jump straight to a variety, we first have to define an algebraic set. Imagine you take a bunch of polynomial equations and you go looking for all the specific spots in your affine space where those equations equal zero at the exact same time. The resulting geometric shape you get, that's an algebraic set. It's literally geometry born directly from algebraic zeros. This brilliantly illustrates the core of Hilbert's Nelstal-Satz, which is a totally massive theorem in this field. It shows us this precise one-to-one correspondence. We can actually reverse engineer the relationship between a physical shape and its underlying algebra. You start with a geometric closed set, then you find all the polynomials that vanish or equal zero on it. And finally, you map that directly to an algebraic ideal. An ideal is essentially just a highly structured collection of polynomials. It's like having a perfect translation dictionary between two entirely different branches of math.
So, now we're finally ready to define an affine variety. An affine variety is simply a non-empty algebraic set that is irreducible. That just means you can't break it down or express it as the union of two smaller, distinct closed shapes. Think of an affine variety as a foundational, unbreakable building block of geometry in standard space. It really is a fundamental atom of algebraic geometry.
But we can't stop there. We need to upgrade to projective space, where our equations stretch to infinity. Let's see how this builds about our foundation, because standard affine space, as elegant and perfectly defined as it is, has a really critical limitation when we push geometry to its absolute limits.
Consider this. What happens when our lines and curves stretch to infinity? If parallel lines never meet in standard affine space, how do mathematicians elegantly solve for those missing pieces out at infinity? It's kind of funny, but Renaissance painters actually figured this out first with perspective drawing, forcing parallel lines to meet at a horizon line to trick the eye. While in pure classical geometry, we want those parallel lines to intersect at that horizon too. But standard affine space just can't do that mathematically, so we're going to need an upgrade. And that solution is an incredibly elegant upgrade to projective n space. Suddenly, we are no longer looking at fixed, isolated coordinate dots. Projective end space is a set of equivalence classes. We're identifying points that lie on the exact same line passing through the origin. So instead of looking at individual dots, we're now looking at entire lines of sight emanating outward from a central origin point.
To make this work algebraically, we use an equivalence relation. In this new space, an n-tuple of coordinates is completely equivalent to that same tuple multiplied by lambda, where lambda is just any non-zero value. Scaling your coordinates gives you the exact same geometric point. It is all about perspective. By doing things this way, we're able to add a pointed infinity for every single possible direction, smoothly and seamlessly completing our mathematical universe.
Now moving into defining projective varieties and homogeneous coordinates. Because we have this totally new type of space that wraps around infinity, we're going to need a new way to define our algebraic shapes.
Here's the catch. Because our points are now equivalent by scaling, standard polynomials just won't work anymore. If you take a scaled point and plug it into an equation that has mixed degrees, like, say, x squared plus y, the math totally breaks down. The zero disappears. To fix this, we have to use homogeneous polynomials. This means every single term in the equation must have the exact same total degree. Doing this guarantees that if the equation equals 0 for a specific point, it will also equal 0 for that entire equivalent line of sight.
Which finally brings us to the projective variety. It's the zero set of those homogeneous elements, forming an irreducible algebraic set in projective space. So if you think about it, a projective variety is simply our unbreakable geometric shape, just like the affine variety we talked about earlier, but it's been upgraded to live in a space that perfectly handles infinity.
So why do these varieties matter as a classical foundation? Let's take a step back and synthesize all of this. Why is grasping both types of varieties, affine and projective, so absolutely essential for anyone seriously studying this field?
Looking at this structural dichotomy laid out here, affine varieties give us our standard, rigorous baseline. Projective varieties take that foundation and upgrade our coordinates into equivalence classes and our polynomials into homogeneous ones. And why? All to elegantly handle perspective and that infinite horizon. They really are just two sides of the exact same geometric coin.
What you really should take away from this is that these varieties aren't just dusty old classical concepts. They are the essential dictionary we use for translating algebraic equations into visual shapes. And, maybe more importantly, exactly as Hartshorne designed his book, these varieties serve as the fundamental training ground. They build up your geometric intuition so that you can eventually tackle the intensely modern, highly abstract mathematics like scheme theory and cohomology.
I want to leave you with a final thought to ponder. As higher mathematics becomes increasingly unmoored from physical reality, we desperately need these foundational anchors. Without these classic affine and projective shapes serving as our intuitive guide, how could we ever hope to navigate the purely abstract spaces of modern algebraic geometry? Thank you so much for joining me on this exploration of Hartshorne's foundations today. Keep visualizing and keep learning.